What is a function of v? Totally random. Totally random. Hello, no name. Aprilia, yeah. Arch Linux. How do we apply my function? I should just, element wise, I should just have an access to flat, I guess. Let's make this a reference. And flat in. And I want a flat out, which is of course not const. And then we run over yeah, all elements. Must have the same shape, of course. Do I need a constant and non-const flat accessor and a shape accessor in Tensor? Yeah. See the shape I really need to make a shape type, come on. Which is exactly the same as index. Oh no. Nah, using const references bullshit. Because I always pass a initialize list actually. So I could call this a shape, but I can't because it's actually a freestanding function. Not even a part of Tensor. Yeah. So accessible shape. Flat. Don't tell me I have to add a type of flat as well. I guess I do. Hello, David and Sam. Yep, what shall we do next? Let's try to just print A of R, which now should work. Or 2. Declaration of const auto-reference flat in is no initializer. Oh, there's a semicolon here. The values should be, I think this one, yeah, 0.59326992, 59327, it's good enough. And the other one is 0.59688, 0.59688. 4. Yep. It is working. Next step. We repeat the process for the output layer neurons using the output from the hidden layer neurons, as in, here's the output for 01. Okay, I need a new weights matrix, I guess. Yeah. So we're going to rename the weight that we currently have. So typically they would call it output to hidden. Sorry, input to hidden. The weights for the input to hidden. And this is actually H, output of H. No, not really. It's the intermediate function. I'm using, I'll put the sigmoid function way up here. I'm going to use it. And then I'll just make here, I guess, A of that. And then we have another matrix, which is let me add a bias first. I think I just have two scalar biases. Oh, I'm gonna make it a vector, even though it uses the same value. B1. Mm-hmm. other hand, no. Nah. I want to store it in the weight matrix. It's not really a weight matrix anymore then, of course. Now it's a weight matrix plus bias. So I'll just call it WB. And now hidden to output. Hidden to output, it looks like the same thing because you have 3 inputs again, and again 2 outputs. So also 2, 3. Substitute that with that. So the 0.15 is 0.40 now. 40. And then we have the 45 replaces the point. I think it belongs to this one. Yeah, that goes there. 45. 0.60 for the bias. And then the output is equal to, again, Sigmoid function on contracts. There was a B here, which now becomes the WB hidden to output, comma H, comma 1, comma 0 still. And let's print that in as well. Okay, I see it. Yeah, this output here is the multiplication. There's just H1 on H2. So we're missing this one here. Oh well, so this is H1 and 2, and I have to make it a vector like this one, so 3 elements. So you can say H0 is H12 0, and H1 is H12 1, and that makes you wonder if I shouldn't call it H10. But yeah, it's 1 and 2 here, although I'm starting at 0. Still, I think I'm going to rename it 01 here then. Yeah, no, I added the 1, and this one has an output of 0.7513. See if we can find that one back. Yeah, 0.751365. 1365. And the other one is 0.7729 something. 772928. Yep. Calculating the total error. You can now calculate the error for each output neuron using the squared error function. And sum them to get a total error. So I need a target, the same shape as my output. And you know the shape, it's a vector of size 2. And the first value is 0.01. And the second value is 0.99. It's that value. Now I have all the values. Yep. And what you're going to do is subtract target minus output. So we can do auto difference is target minus output. I think thou cannot subtract two tensors. Oh, that's right. I have to implement that. Yep, that looks good. Oops. And then we want to square that. So let's make a new function. I think I make my functions const, can I not? Another function called square. Yeah. Now, does it look like a square? Yeah, I think so. 0.7413 squared is 0.549. And then, of course, 0.217 squared is 0.047. Seems to be correct. Then we need something to add that together. And that's a loss function. Thought I was dividing it by 2 as well. The sum, yeah, it's a half of target minus z squared. The half is included so that the exponent is cancelled when we differentiate later on. AKA pretty arbitrary. Or can't I? How can the loss be negative? Been adding the wrong stuff. Been adding the wrong stuff. Let's do it like this then. Let's call this the sum of differences. No, the square of differences. I need the square of that. Don't need to print it. Zero 0.28371 29. I mean 298. Yep, 0.298371. That was the forward pass. Now we go to the backward pass. Our goal with backpropagation is to update each of the weights in the network so that they cause the actual output to be closer to, I guess, the target output, thereby minimizing the error for each output neuron and the network as a whole. Mentally shift, how are you doing? Yeah, I guess you should go then if you need sleep. It's always a good idea to tell yourself that you should go to bed, theoretically. Let me see what they do. Are they calculating one thing? Total derivative stuff. Out 01. That's 5. Yeah? They calculate the net 01 is a bit weird. Yeah, well, okay. Anyway, it's relative of the weight number 5. Then we get numbers out of that. And what I want to do is fake it. That's the whole reason I wrote this program, really. But they have intermediate values. Like the first intermediate value here is the, oh, that's actually a total? No, that's relative to out. It's not easy, is it? Well, I can just do the whole thing. Who cares? So what I'm going to do is I'm going to change W5 with a really tiny little bit and then recalculate the stuff. So we did all that. Now W5 is, if you look at the image here, that one, it's the 0.40, which is this one. So what we're going to do is change this value with a tiny little bit, not tiny, let's say 0.0001. It's really tiny. I hope this still it must fit in a double, right? I'm working with doubles, so. And then we can recalculate everything after that. Let's make this a scope. To do everything after that again. I think I want to have a bigger precision here. I don't know how that works. Oh, I don't know how it works. What can I close? Because I don't want to. No, this one can be closed. Totally. Let's click on that. I'm going to search for C++ print double with full precision. And then they come with standard format. Dude. Set position 0. Interesting. More formats. This is a better one probably. Still keeping it. So just not fixed then. Let's see if that works. So from here on I want to print full position on send it out. We need for that limit. Limits, I think it's limits, right? Include limits. Yep. Now we get huge numbers. You should do it at the top so you can see that one as well. It's printed, why not? So we're giving W5 a tiny notch. You see that it changes. Basically nothing, just exactly the same, this thing. That is not changed. And this one, that is changed. And of course the loss function is also changed. Tiny little bit. So we can fake here the partial derivative between the loss function relative to weight 5. Okay, I should be able to print that now. Why don't I have to keep the loss function? Duh, really? Okay, let's just remove the scope then. Output 1. The target is the same in both cases. Don't have to repeat that. That depends on the output. SD1. So loss 1. Yeah, now I'm numbering it 02, but actually it's a vector, output vector with both 01 and 02 in it. I should not use 1, I think that's too confusing. Let's call it A. And then of course the other stuff as well. So the SD1 and the loss. Substitute SD1 becomes SD underscore A. And the loss one becomes loss underscore A. And then I'm just going to redo everything again, right? Everything? Well, not everything, but close enough. P. Target is still the same thing. Make that a const. Can't make it const if you have to assign it afterwards. And those are the same values. Yes, that is all the same value. The loss is even the same value. I believe it. Right, to the delta loss. I need a delta. I think I have deltas here. I had very, very long discussions with ChatGPT. Oh, not this. That one. Let's find a D there. The D thingy. There it is. There's one. There's one. To the derivative of loss relative to W5 is, and now we fake it, so that would be loss B minus loss A divided by the delta that we added. If you get what I mean, that should work. Now, let's see if that makes sense. 0.08. Yeah, there it is. The total, that's our loss. The partial derivative of that by with relative to W5, 0.0821. Wow. 6.7. It's all the way up till here. Thought it worked like a charm. I just thought we just changed W5 a little bit and then recalculated again forward. And then, of course, we have the partial derivative. If you make the change small enough, you calculate accurate enough. So that's fun. But they did it differently. They calculated it differently. I'm very curious how they did it. They have 1, 2, 3 numbers that they multiplied using the chain rule. Delta E total delta out 01 times delta out 01, or delta net 01 times delta net 01 over delta, or D, sorry, it's just D, I think, dW5. And that one is there, that one is there, and the 0.74136. That's here, right? Yeah. Well, it's called back propagation, so I guess we should start at the end. And this is the end, right? It's E total, and then the immediate input of that. Derivative of the loss function relative to O1, out 1. Yeah, because as we saw, W5 has no influence at all on EO2 because it has no influence on out O2. You can also see that here. W5 only has an influence on O1, but not on O2. So a partial derivative of dW5 is going to be 0 for this. dO2 over dW5 is 0. And now this is the partial sum. So that is half of the target O1 minus out O1 squared. And we can calculate a partial derivative of that relative to out O1, of course, which would give off to the top minus out O1, I think. To the partial derivative of E total over the out O1 should be equal to a minus out O1, I think. No, the target does not drop out. You put the 2 in front of it, it cancels out, and then this becomes a 1, and you just, the whole thing is left. So it's this. Oh, and then times -1 because of the, yeah? I think so. Yeah, this -1 here. I want to do the whole thing in at once. So this is a single value, which we get a vector somehow. This is the result that I find is out minus target. But might as well do all the outputs, no? It's really just 01 minus, yeah. I was writing it in a different file, so let me try to update it. Yeah, here's my documentation. And I have a loss function that is 1 over m, so yeah, that's the half. No, it's not a half. Actually, it is a half here, but let's just work with this. Since they have 2 inputs. Let's work with this formula. So the loss function, is function of z, and where z is then the final output. Yeah, so the z here is equal to the out thing here. Is the sum over all the elements of the target as well as the element over z, and then the difference of that squared. And it really doesn't matter if you do z minus t or the other way around. They have it target minus out, so I have out minus target. But yeah, we square it anyway, so who cares? And this then comes back later on in the form of the gradient subscript z of L, where L is the loss function. But then, yeah, it is still a scalar here. But the whole thing here is, I think, two-dimensional things. It's a vector. At the very least, I can begin with that. I must say, I was asking ChatGPT, last thing that I asked was, is this the correct order, or should we reverse it, you know? Just so put this vector on the left side, and then that one, that one, that one. And then it immediately agreed that that was the solution. But I'm not so sure. So let's see what these people are doing. So this here is our gradient ZL, and the 0.741 is put up front. So it is indeed the other way around. It doesn't really matter, of course, how you multiply those things, but I kind of begin with this one, so might as well put it up front. And of course, it comes from the way that they calculate the partial, or the way they write the chain rule here for the partial derivatives. And they start with the output up front. So maybe you should do that as well here. It's probably more common, if you get what I mean. So we begin with that, and then that one, and then the third one, and then the last one. And I want to keep track of all the dimensions. I think it's probably a good thing to start with an abbreviation. So these are all matrices or tensors, things between brackets. But we can write them also as, as the elements of a tensor. So maybe we should something like note that, and then go a little bit deeper into the structure. So this thing is, I should first write something about the notation. Notation. Let's write the elements of a gradient matrix tensor. That was also an idea of ChatGPT, and I forgot what exactly it said. Find that back. This chat has become way too long. Yeah, it's we're always already past it, I think. I have to go back. This one. That thing here, so you see it writes this as that, so the L just kind of drops out, which might be annoying, but it's also shorter to write. So I'm going to use this for now. I can just copy that, I think. So abbreviation of the gradient tensors as, what the elements of the gradient tensor is delta. Yeah, well, and then the gradient, for example, z. And then I want a subscript, and I have a subscript here, I. But maybe not clear enough, so let's use the other one. Let's use W. And that actually has I as well as J and K. And I close that, I think. TF8 subscripts. Nope. Damn it. Subscripts also not. I had a bloody page open. So they don't have the alphabet, but if you wanted to, then there's a lot of them. Subscript 2. What the hell is that? Jesus, I have so much. But don't ask for a subscript Q, because they don't have it. It doesn't exist. They never added it. It's ridiculous. Okay, it's not working. UTF-8 subscript J. Now we're talking. That's what I wanted to see. J. And then subscripts. Subscripts. Oh, it is all that there is. It's really not a lot. But thank God the J is there. Oh, wait, I need the K. Back K. Copy the K. K. WIJK. Meaning that like this or that. The U here is implied. So that's about the notation. Then we can write that the gradient relative to Z of L is a matrix existing of, I think, one dimension. So we're going to write that as delta ZI. Yeah, with the size of M. Just write it like that. I think, you know. Not really true. This must be a row vector. So maybe I should use a J here. Let's think about this. Damn it. So this is a gradient relative to a Wij of a scalar. So that's going to be a matrix with the shape equal to the weight matrix, which is output cross inputs. So that would be that. I think I already have written down what W is. Yeah, weight matrix, shape M cross N. So you have N inputs and M outputs. I have 6 viewers. I'll go over my whole text here from the top, so you know what we're talking about. So this is about calculating the gradient matrix. If we have a single layer, we have a single weight matrix. Yep. I'll use this website here to make that clear. In this case, we have 2 layers. We say we have 3 layers, but not really 2. The first thing is a fake neuron. This is just the input. So you have a hidden layer and an output layer, 2 layers. And as you can see, each layer has a number of weights. Yeah, this layer has these weights and this layer has these weights. And even though they are written down above each other, it's really a matrix of 2 by 2. So you can have a matrix of 2 by 2 and you can multiply that with a vector of 2 elements, and then you get a vector of 2 outputs, this one and that one. And then another weight matrix here. So we have a single layer, then of course we have a single weight matrix. And that is going to come with a single gradient matrix, which I want to calculate. And that has the same shape, so the same number of columns and rows. In fact, what we're going to do is consider a single layer with n inputs and m outputs. Okay, so in this case we have 2 inputs and 2 outputs, or you can count the bias as an input as well. Then we have 3 inputs and 2 outputs. And here I do it abstractly, n and m. Then the inputs are called x, yeah, they call it I, but well, which is a column vector of size n, because you have n inputs, of course. And the weight matrix, W, which is the shape of m rows and n columns. And we have a bias B, which is a column vector of size m, but probably better to just treat it as another row of the weight matrix, but okay. We have an activation function and we have a loss function. Now, for example, for the last 2, the activation function could be the sigmoid function, 1 over 1 plus the exponent of minus v, which is applied element-wise on any component of v. Yeah, so if this is a vector, then the result is also a vector. It's a matrix, the result is a matrix. Just every element we do that. Squash the output between 0 and 1. And loss function, well, many loss functions also, but we work with this one. It's defined as 1 over m, it's the number of outputs. And then we run over, I runs over all the outputs, and we just take the difference. So the actual output minus the target output, difference of that squared, all summed, and then again divided by. That's the same thing as I did here, the arrow function. Yeah, they take target minus output, square it, sum it, divided by 2 here for random reasons. We divide it by m. So t is the target, is part of the training data. Now you give it a certain input and you say, I want that to be the output. If the neural network is fully trained, and it's possible, then it will generate the correct t values with the given inputs for all the training data. So in fact, these t's are vectors, output vectors, that are a function of the input, but given, given as part of the training data. Then I'm going to write that the loss, that's called loss, here it's called error total. Yeah, other places they call it loss function. Is the loss function applied to the activation function applied to the weight matrix times the input plus the bias. Or we can do that in 4 steps. First we calculate W times X, and I call that U. Then we add B, and I call that V. Then we apply A, and I call that Z. And then we apply L, and I call that L. Then that's loss and L are the same thing. And then, and this is not explained, but yeah, you have to just picture that you really go down in the direction where the thing is the steepest. So this gives you that direction, the steepest way to reduce L. You want to bring the loss function to 0. Note that the loss function is a sum of squares, so it's always positive. So if you reach 0, then you are completely done. You have a perfect neural network, perfect weights and biases. And the fastest way to get there, I mean the steepest downhill way, is given by this, which is the partial is a matrix, with the same shape as W, which exists of elements that are actually just a partial derivative of the loss function with respect to each of the elements of the weight matrix. So you can write it like this, or you can write it like that. Same thing. And alpha is a small value because you want to take small steps. You go downhill. If you take a huge step, then maybe you're standing on the opposite hill, going upwards again. So you want to go slowly down, so you don't overstep something. So it's just maybe not too slow, because you'll never get there, but definitely also not too fast. They call that the learning rate. Yeah, and this is kind of an underscore W, it's kind of a LaTeX notation thingy. So nabla is usually used for gradients. And then the subscript W means with respect to, W. But you probably just better to think about it like that. Already have the notation here. Right, so this is the gradient matrix with these elements, which are actually that. alpha small value that controls the magnitude of the update. Can be too large because then one might overshoot the target and or end up way past the point where the gradient is still more or less the same. I mean, if say your valley is looking like this and you are here, then the gradient is like this steep. It's a straight line. But if you take a huge step, then suddenly you're already in a horizontal part. So yeah, you kind of want to take steps that are so slow that the gradient doesn't really change a lot, I guess. And then we're at the bottom. This is the last stuff I wrote. So then we realize that we can write this gradient with respect to the weights of the loss function, which gives us this steepest direction within the weight space that we can go to in order to reduce the loss towards 0. As using the chain rule, yeah, going from there to there to there to there in steps. And we just saw that the weight itself is a matrix of m times n. So if you then want to subtract something, then that something, of course, must have the same shape as that as w. So yeah, also this thing here, alpha is just a real number, must have the same shape. So this has the shape mxn. And now the other things are also matrices. So this thing here must be I don't know. It's actually a good question. I thought it was a vector, but we're not ending with 1. Maybe we are ending with 1, because I think that this is a 3-dimensional tensor, the last one. So it's probably the smarter thing to do is consider it all to be 3-dimensional. And then, of course, you don't know where the 1 is. Is the 1 on the beginning or is the 1 at the end? Or in the middle? But yeah, that is exactly the question, isn't it? Maybe you can think about it just by looking at what it is. This is a scalar and this is a gradient relative to z. And z is simply a column vector. Well, that means that the gradient must be a column vector as well. Not sure. Totally not sure. But, well, we can try. So a column vector would mean that we have rows and we have only one column. The rows is first, so if we would write down m, I'm just going to use the same shape as that one. So it's basically m x1. Okay, if we, as long as we stick to rows, columns 1. And then maybe another x1 or maybe another x1, I don't know. But these two already give it pretty clear what that it is a column vector. At least it is this way. But is it a column vector? That's the question. I started to doubt it. It was a column vector when they had it the other way around. I think actually it has to be a row vector if you ask me. This thing is an m. Oh, what the hell happens? Undo, redo. That is an mxm square matrix, and this one too. So I can hardly go anything wrong there. So yeah, this you can only multiply that one with that one if it ends on an M. So I think it must be one. Oops, must be 1xm. Otherwise, this M does not connect with that M. So now we can connect this M with that M, and this M with, well, another M here. M, and that drops out. So then what we are left with is then, and here we get 1x. Yeah, because the 1 is left. That one drops away against that. That one drops away against that. That one drops away against that. And then what is left then must be what is left here. So it should be mxn. I think. Yeah, something like that, right? So we write that in the delta form, then this thing here is actually row column I j. That's all the way. That's how I use those things all the time. So I'm going to put a j here, I think, to make clear that it is a row vector. And now we do the next one. So that is written as delta, and then we just use the v. And this is, well, ij. With the shape of mxm. So a matrix. This shape mxm. I just wrote that down, but yeah. And then we get this one. We write that as delta u ij. I mean, I'm not feeling certain about this, but it is extremely important that I get it right. Because if I make a mistake here with, you swap something or you just make some mistake, then it's going to be such a headache later on. But okay, I think it's correct. I double checked everything up till here, up till this line, and that must be really correct. So only this is dubious. Still, same thing. And then we have the last one, which we wrote as delta w ij. Okay, I think. Oops. Where is it here? Okay. Which is then that right. Well, yeah, that is just notation. So I think I want to, or have to, or can also write down element-wise partial derivative notation. So, for example, in this case, this is the dl dzj. And this is then the z. Now L is a scalar, but z is not. So z has an index here. I don't know which one yet. Delta v. V is also just a vector. So yeah, one is I and the other one is j, because I think so anyway, you know, it's never clear, is it? I mean, why would a k drop out? Okay, that's why I'm writing the program to get a feel for these things. I think right now I'm just going to put an I here, a j here. So the vj looks not nice, does it? Because this is zj now, and then this is zi. Why? Kiriakum, hello. Man, I don't know what to do here. I just don't know what the correct initials are. Actually, maybe it's kind of silly to use a j here, because v is said to be a column vector, which means I should use an I. On the other hand, if you just have a single index, I want to use a j here. Why? Because it's a row vector. And for any given y, it's just, sorry, any given j it's just the I of the z. How about I use an I here? And then we make clear that it is equal to this j. I think that might be not too bad. Go back to my subscripts. I think we have an equals. Copy that. Equals j. Right, yeah. And then here it's not really clear if I should use j here or there. On the other hand, if I do this, I mean, also V is just a column vector. It's no difference with Z. Both are just column vectors. So why would I use an I here? Because if I do this, I should write here also I equals J. And that looks very weird because we already have an I in use here. So maybe I should not do that. I should just use J. But yeah, then I use J here to signal that it is a row vector. Which it is, of course. Maybe we should do 0, 0J. Of course, I write it like that. Not a bad idea. Let's put a 0 in front of it. Yep. Yeah, because I see it as a matrix of 1 row and m columns. Then the row is, of course, always 0. But then I reuse J here as the row index of the column vector Z. This here is then IJ, I guess, whatever, IJ. Can do it like this. And this is the V. That's this V. With some index, well, it's still V. I don't know if the I and J must be swapped or something. I don't know, but let's fill something in. Derivative of U. And U is also a column vector. It's okay. Put like that. And this then is so that is U. I delta W, and then very strangely JK. I don't see a K quickly. Let's go here. K. Oh, that's my K. Of course. Yeah, so I already mentioned that here. No, not only that, and here we have L relative to W, and we don't have that here. That's the whole thing. So no, this is not correct anymore. Or I have to put the L into it as well. I could call it LW maybe. Nah. Not really sure how useful the delta thing is here. Probably just confusing. I might as well use this all the time. Why not? What does it give me that I use this notation? Okay, so I only had this here so I could copy these things, but I kind of copied them from the website now already anyway. So let's delete this. And this starts to be duplicated and old. Well, not really. Here we have something written out with an example. Might come in handy. This, however, is nonsense. There's no way to solve this. A nonsensical attempt. Well, thank God we have kind of three inputs here. Yeah, we just see the bias as an input. We have three inputs and two outputs. So we can keep them apart and then maybe use this as example. And then if I write things out, I hope I start to see the light, how it really is or should be. Yeah, so get the bias, but we do as if we have three inputs. And then we make an example. Let's keep it like that. For the simple case, we do not have a bias nor an activation function. It's maybe not the right thing to do. No. No. let's look at yep, is that correct? And it's still the inputs and inputs and outputs. Yeah, well, throw away a few things, I guess. So that's this is calculating what happens when you multiply the input with W. That's U. But we don't have a B anymore. Might as well go to V directly. Is that nonsense? No. Let's go to U or V. One of these drops out. I think we're going to use V is WX. Sure, yeah. Okay. So the bias gets included in W. Let's say I go straight to V, okay? Or maybe not. Probably better to use U, otherwise I don't understand this anymore. I'm just going to assume that the weight matrix is that big, and then the results must be U. And this is just something we're going to skip. Meaning I'm going to assume then that B is 0, so V and U are equal. It kind of doesn't really matter what I use, I guess. let's use V. But basically V and U are the same thing now. Right, then we get V. Yeah, the output is two-dimensional. I want to move it down. I should not have removed that one. So this becomes a 1. And this is that thingy. That is this thingy. And this must be in subscript 1. Yes, the inputs are now x0, x1 and 1. So this must be a 2 by 3 matrix. So this whole thing must be removed as well. Great. Keep moving stuff. In fact, I'm just going to remove the whole thing in the middle here. No, wait, I want to keep that. I want to keep these things alive, and I'll move that there. It's not easy. I'm just will copy that, I guess. And then this must be gone. Now you have to move this down. Yeah, this is also two-dimensional then. Let me just move this. W00 times x0 plus W01 times x1 plus W01 times 1. Yeah, I can put the dot here, I guess. So let me put a 1 in as well. Or even the dots. Nah, let's keep it like this. And then again that and that and the 1, sure. be 1. Why the hell do they start counting at 1? So annoying. Right, so x0 is 0.05 and x1 is 0.10 and this is just 1. And then the W0 is is 0.15, right? And then that one is what gets multiplied with the 0.1 for the contribution of the top output to this thing times that one, right? 0.2. So put 20 there. And this is then 0.35. And here we have that is the bottom contribution that is multiplied with 0.05. So that is this one, 0.25. That would be 0.30 then. And again the 0.35. No, which then becomes 0.15 times 0.05 plus 0.20 times 0.10 plus 0.35. That would be the bias times 1. Yeah, leaving it out to stress that it is just a bias, as it were. Now, what do we get here? I'll do it with my calculator. 0.15 times 0.05 plus 0.2 times 0.1 plus 0.35 is, yeah, I recognize it even. This is our friend 3.775. And then the other one was 3.8 something. 0.15, that's the same thing. I should just add 10.10.1. 0.1, that would be 0.4. No. 0.1 times 0.1. So this is 0.3875. Yeah, well, you get only to see this one, but the other one is hidden. But that's what it should be. Yeah, the thing has 2 layers. I'm afraid we just have to do it. The second layer then gives and now we fill in here the output that we previously had, but after doing the activation function. So really, it's going to be the activation function of V0. And here the activation function applied on V1 as input. And again with the 1. And these are different weights. Nah. No, I'm not happy now because how should I call these things? Okay, the output here is anyway output. I can copy that. Although here they are called outputs is 1 and 2. 5932 69992. And that one is this one. 59688 4378. B2 is 0.6. Okay, so what is this weight here? That would be 0.40. Yeah. And then we get 0.45, 0.60, 0.50, 0.55, and again 0.60. Yeah, I just believe it. Just copy it from here, I guess. So that would be this one, 0.75136. 507. And this one, 0.772928. 465. Why is it one longer than the other? Nope, refuse to do that. 7. Right. Still does just forward shit though. Yeah, the loss then becomes well, what we do is Z minus target. I'm not going to change that. So this is in this case O minus T 0 squared plus O1 minus T1 squared all divided by 2. Which is let's see. The target is 0.01. 9. My calculator says it's an 8. I believe my calculator. Anyway, it seems to work. But that's not interesting. Interesting is the gradient stuff. And the first thing they do is calculating this one relative to out O1. So the arrow function relative to an output, that would mean a loss relative to the output, which is this one. So I want to define that with Z replaced by O. It looks a bit silly though. It's not a complete matrix, so maybe I should use the gradient notation. It's not a mathematical notation what I have here. So we want to use that one. So we have a real gradient minus the arrows on top of it. Well, yeah. So let's do that, but then O here. Or I could say some matrix like that, maybe. But yeah, doing that notation, I maybe should do that here as well. Going to remove this because I already have it at the end. Okay, now what is this? DLDO0. Where this is L, right? So that becomes this constant, so that drops out as 0, and then this 2 drops away against that one, so we get just this. And I don't get a minus in front of it. Mahaha. So it's just that. And now we have too many spaces. Let's remove a space. And then we have here the other one, of course. Different elements. No, did I do that correctly? I think so. Let's fill in the numbers immediately. So O0 minus T0, that's just this value here. So that is 0.74136507. And then we get that one minus this. So that becomes, I don't know, negative 0.22. 0.77292847 minus 0.99 minus 0.21707 153. Hopefully we saw these numbers as well somewhere here. Well, I get this one, 0.7413 6507. The other one they don't show. So incomplete. Unbelievable. Yeah, well, that's why I'm doing everything over. Because we need all the numbers to get the right picture. Then I guess next is the out the net. What that is. No, and the next one would be no, there was always was Z before or V, something with L, Z. Then the next one is this, but we skipped that or we skipped the U here. I think we get this one. I still have the V. Let's not do the V. Let's not do the U, I mean. Oh, undo. For that one then. I think that Z must be the O then. Or not. What is this? Damn it. It's confusing. So I replaced V. So O is V, really. Oh, so we have that here already. But. Oops. I went straight to that one. V. So now I need. Sorry. So I skipped Z. No. I'm going to skip stuff. Oh, we start at the bottom. Wait a minute. I'm here. Yeah. So now I replace Z with O. So now we get O is AV. And we skip U, so we get just O is AV. This one. And then for the gradient, that would be the one next to L. So that would be indeed this one. O is AV becomes here delta VO. Nabla VO, I mean. Yay, that looks better. Now we have something that drops out. This O against that O. Still scary though. This is an O relative to V something. No, we should have that where the O was Z, right? So looking for delta Z, delta V something. This is C divided by V. This is L divided by Z, and then we get Z divided by V. Here we have L divided by O, and now we get Z divided by V. And this one was L divided by Z. I keep forgetting that. L divided by Z, yeah. So the Z has changed into an O. And now does it look like it makes sense? This L here is up front and this O here is up front. And then this O here is at the end and this V is at the end. Totally makes sense. Yep, and then what the L did, this is a J here at the end. So, yeah. This is just ij. And I use save a spacer to line it up. Poo. Okay, now we can split it up because we have now an A, an I, and a J. So this is a matrix. Let's make it a matrix. And then we get, of course, IO, and this is, of course, 0 over delta V0. And then again, but the column has changed, so that is the J. So this must now be a 1. Yes, because I is the row. So if you go down, then the I changes. No. J is the column. At least if I did that correctly, because I kind of put the I and the J here, but maybe it's the other way around. We'll see, I hope. I should go to bed. I think I'm calling it a day. Well, yeah, I usually say that and I continue for another hour, but well, it's the intention to stop very quickly. Can I calculate this derivative? What is V? You're talking about ZV, right? This one. This is actually illegal, right? You know this. V is a vector, but you can just write a vector in the exponent. And I'm kind of, like, well, okay, you do that X, you do this element-wise, then. I think it's yeah, you can write it like that. Anyway, then we get here, of course, the derivative of I can even write it out completely, I suppose. Maybe I should. I think V is a column vector. Probably. I'm not sure. Yep. So then what does this become? This becomes the derivative of O relative to V0, but O0. What the hell is O0? Here's O0, here's O0. Nah, what? I completely lost it again. Oh wait, here it is. Yeah, so this is simply equal to O, in other words, O0. I think I'm going to use spaces when it is a matrix, like here, and no spaces when it is a vector, like here and here. O1. Where's my 1? Here's a 1. Yeah. So we simply have O0 equals that, and therefore this is then the derivative of A for the value V0. Yep, which happens to be A times 1 minus A or plus A. What was it? Minus, I think. Yeah, minus. So if you have an activation function, the sigmoid activation function, also called a logistic function, the derivative of that is itself times 1 minus itself. So it's like super easy to calculate. As I say here, so the partial derivative of the logistic function is the output multiplied by 1 minus the output. So output times 1 minus the output. So no reason to actually come up with the formula for that. I'm just going to express it in A itself. So we have the A of V0, that is this function, times 1 minus A V0. And then that is the derivative. That is the derivative at V0. So this whole thing, if you replace V0 with whatever, then you have the derivative actually of that. Obviously with respect to V0, right? That's what you want to do here. And then the other one, with respect to V1, well, it's not the function of V1, so that becomes a 0. And here we get, yeah, also a 0. And then the same thing, but then for V1. V1. Where shall I put my 0? I don't know why. It looks better this way. And this is a matrix, so I'm going to add a space here, because I said so. Yep, I think we have it. At least for this example. Now I can fill in the numbers, I guess, for this one as well. Okay, so here we have V0 is this, and then the activation of that is that. So AV0 is this number. So this is that times 1 minus that. And then a 0 somewhere. And here the other one. Oh no, it doesn't fit. There's going to be a major mess. Actually, I'll just have to delete this, I think. And then cut it off. And then paste it here. Maybe with an equal sign here. A repeated equal sign. And then shift this up again. And then put the 0 over the 1 for some reason. And then close it. Space, close. And then we can actually calculate this thing to be there we go again, the calculator. 0. Yeah, okay. Now we're going to see one of these numbers back. I doubt that it, but you never know. 0.3519. Let's see. Hmm. No. Oh, yeah. 0.358916. No, it's a different one. Well, I don't know. I think I did not make a mistake. But the number doesn't pop up here. Let's look a little bit more specific. Oh, wait a minute. This is a completely different number. 0.75. Oh, I've been using these. I should have been using those. Yeah, so I made a mistake. Unbelievable. So I did do it wrong. I should have been using that number. What? And calculate it again. Would have been nice if I had a calculator I could base into, right? Like, base that. Do I not have that? Can I not do that? PC? Nope. What about multiplication with BC? Yep. Way easier. Which is this number, 6815602. So I should increase the precision, I guess. And then the other one becomes that. Ooh, something missing here. What the hell? Yeah, the other one is not given, I think. Good thing I checked it. Mm-hmm. Why did I make that mistake though? Because I took V0 here, which is quite logical if you have a V0 here. We should have taken that value, which is actually O0. It's already activated and everything here. It should be, yeah. So it's the A of O0. A of O0. It's not V0. Why? Can we make sense of that? Mm. No, cannot make sense of that at all. Shit. Makes no sense. It makes no sense. The thing that goes into the loss function here, so what we subtract t from, is called z here. And that is what goes into the loss function. And that is what is returned from A. Oops, that's a bit too far. So what goes in loss function here is O. So O and Z are swapped. Z is replaced by O. Yeah, we use O instead of Z. That's totally correct. So we have O is AV. Totally. It's the only thing we can make of it. Except of course that V is not this V. I replaced the V as well. The fact, this looks so symmetrical. Looks like O, V was replaced with O. So what is replaced with O? V or Z? Oh, right, I made a mistake here, I think. This is the weights thing times the input. So this is my x, that's the output of the previous layer, including a bias, multiplied with the second weight matrix, and that gives a u. And I replace it with an O, which is not correct. O is after activation. So at this point, it's not O. So the activation here means that I switch to Z. Let's see. V is a result of W times X. It's not, it's U, but I skip U and it goes straight to V. And then we get Z is the result of the activation function. Yeah, I need to replace a V with something else as well. Pick something. If well, let's kick the U out. Start at the top. Z is replaced with O. L stays. O. O. V is replaced with F. Z was replaced with O. V was replaced with F. Z was replaced with O. V was replaced with F. W is replaced with Q. W is Q. U is V. W is Q. The second layer then gives us, where I use 001 instead of 012 from the website. So we're still calculating forward here. Yeah, think so. Yeah, so I'm multiplying this with the activation of V, so this must be Z, kind of. This is Z0. And Z1. So Z plays the role of X, like it says here. So this is Z. And the weight matrix times Z gives us F. So this is not O, it's F. And then you can get O by doing the activation, which means we need some space here. Apply activation function, that is now O is A of F. So now we get O. Why did I have a 0 here? A of F. Kiriakun, thanks man. We have F here. I want to check this just in case. So 1.2249 to 1404 with a minus sign. How do we do that? No idea. Times -1. Yep. And then e to the power of that. I can hardly see my calculator. Where's the e to the power here? Where's my flashlight? Yeah, flashlight. I need a light to find the button of my flashlight. Oh, there it is. Oh, it's empty. Well, almost empty. First, the power is there. Okay, so we can do shift this button. Answer is that. +1 is that. And then we do 1 divided by x. Is that. And that is 0.77292847. And I need to put my flashlight on the loader. Okay, so that worked. The loss then becomes, well, that is still correct, because this is the values of O that have been used here, and T. And then we can calculate, so that's what we need indeed, which is TL dO. That's this, which is written out O0 and O1, which is O0 minus T1 and O1 minus T1, which was also correct wording. Yeah, already wrote that elsewhere now. So now the next step is, finally we can recover here, FO is F, you gotta be kidding me. Okay, O, F. What the fuck? This is so error sensitive to errors. It's unbelievable. Okay, this is F. Suppose you do this without this care, and then you just write code, and then of course the code is wrong. I mean, I can hardly get this right, let alone that you can write the code correctly in one go. And then find the error. When you have code, this is doing mysterious stuff. So impossible, completely impossible. So this is the derivative of O. Which is a function of F. So you have to fill in F here. F. And then, lo and behold, the value of F. No, that's the value of O. What? No, no. No, wait. This is already that value. This is the A of F0. This is F0. So the A of f0 is that value. Thought it's correct. Now it's correct. Yep. So maybe I should have written O here. Why am I running A here? Well, because you want to see the A times the 1 minus A, knowing that O is A of F. Gonna make sense, I guess. I can put one extra step, symbolic step here in between though, because the A of F is actually O. So this is O0 times 1 minus O0. And this is then O1 times 1 minus O1. Yep. Now it all makes sense again. So then the next and last step, I literally continued an hour by now, relative when I said I was going to bed. It's sad, but hey, we fixed an error. So the last one that I need is this one. Which is this. Apparently. So I once, I think when I was about 30, I did a test. I just measured a lot of stuff, and it was theoretically for getting a job-ish. And I did score so high that, well, it was a course, C++, I think, with job guarantee. So you would do the course, and then afterwards you would get a job. And I scored so high that they didn't want to allow me into the course. Seriously. They said, you don't need this course. You can get any job you want. But immediately, but the scores that I got on the test was like the maximum for everything. Every point I scored like, what is the skill? It was in Dutch, of course. Let's say excellent, maximum range. But then still they had a difference, and I think that the things that I scored highest on was spatial insight, and that's why I'm mentioning it, accuracy. So I think that the fact that I'm very accurate comes in handy while doing this. And yeah, I often see people work on something or type something, or I don't know, maybe it's just social media, but then yeah, they are so fuzzy. You cannot believe that I would be able to do this without making non-stop errors. Anyway, that's why I have autism, right? So I can do this. So what is this? Derivative of f relative to qjk. That is a three-dimensional tensor. Now write that down. Most of those terms are going to be zero though. Why is there an U here? Should be an F. U should place with F. Not accurate at all, but I found it. What is the F? I did replace it here though. Just Q's and F's on that line. Yeah, so F is a vector, Q is a matrix, and Z is a vector. You can write that out. Maybe I should do that. Probably should do that. And I already did it for W somewhere. It's at the bottom, I think. I deleted it. Nah, really? Deleted it. Right. Finally, using so I have Q times, it's the result is F, Q times Z. And I want to write that out where my Q is the weight matrix, which is so